And we're back, and happy Thursday. Today we're going to switch gears a little bit, and we're going to talk about the geometric distribution. The geometric distribution shares something with the binomial, a lot with the Bernoulli, and a little bit with the binomial. It adds this notion of temporal sequencing of Bernoulli distributions. So why don't we begin? So where we last left off, we talked about stochasticity behaving similarly for many types of systems or experiments. And so we have these common mathematical descriptions for which we can bring to bear certain tools. And now, because we've proven things like the summary statistics, the mean and the variance, as long as we can match the experimental system's stochasticity to one of these descriptions, it adheres to the same properties. And this gives us the ability to analyze, make comparisons, and also to mechanize, and we'll have a lot of experience in this class in mechanizing these things. And like we saw with a Bernoulli distribution, flipping a coin, heads or tails, is the same form of stochasticity as choosing a team member, male or female. Okay, so the Bernoulli distribution had two states, the success state, which we're calling a 1, and the failure state, which we called a 0. And the success state had probability p, and the failure state had probability 1 minus p that we're nicknaming q. We proved the expectation, mu, of a Bernoulli random variable, this two-way outcome, is p, and the variance is pq. We also talked about the binomial distribution, and the binomial was a sequence of n many Bernoulli trials. Each one of these slots, n many of them, had a success or failure, or male or female outcome. And so we take that string of n many successes or failures, and we reason about the probability of having some number little x many successes, or heads. And so we said that probability mass function was n choose x. How many ways can you choose the positions of these x many successes out of these n slots? And then the probability of the successes, there are x many of them, so it's p times p, x many times, p to the x, times q to the n minus x power. And I left it to you to prove that the expectation of a binomial is n times p, and the variance is npq. Okay, so why don't we go on to the geometric distribution? And so let's say we have a sequence, imagine if you will, a sequence of two outcome observations. That could be male-female, could be flipping a coin, but you have two outcomes for an observation, and you have some sequence in time of these. So I'm going to call this the interview problem. Imagine you're here on the right, you're a business owner, and you have some candidates that you're enterprising to interview because you want to fill a job. Now, of course, these candidates arrive in some order, and they're sitting in the waiting room, and they're in order of arrival. You interview them. Okay, so how many people do you interview before someone is hired? Well, let's imagine that resources weren't an issue. Now, of course, in the real world, interviews cost money, and you don't have infinite amount of money to spend on interviewing 1,000 people, right? That never happens. But let's just assume resources weren't a problem. And so you're just going to interview someone up until the point where you find a suitable candidate, and you're going to hire him or her. So how many people do you interview before someone is hired? Let's think about this. Well, were there any restrictions on how many interviews you were able to conduct or how many you can afford to conduct? I didn't set any restrictions. So that's a really important piece of information. In any problem, if there's no restriction set on it, it's a so-called free parameter, so it can take on any value. In this case, you can imagine an infinite supply of candidates that you can interview. So no, there were no restrictions placed on it. So let's think about, did this description say that you had a preference for any particular candidate? Are you going to prefer the third candidate, the second candidate, the first candidate? No, there's absolutely no preference. So there's no bias. The likelihood that you're going to pick the first candidate versus the second candidate versus the third candidate, there's no particular difference in the candidates. So you can imagine this as each candidate having the same probability that he or she is going to be hired or not hired. Okay, so just say no. Don't introduce any additional information to the configuration or scenario describing stochasticity beyond what is absolutely stated in the question, right? So whenever you get a scenario, don't ad-lib other information. Go exactly what is stated, and what is not stated you can assume is a so-called free variable. So let's get back to that question then. How many people can you interview then? Well, how many choices are there for hiring or not hiring? Well, we didn't set a restriction on how many we can interview, so I'm going to say infinity. You have an infinite supply. Now, how many choices are there for hiring or not hiring a particular candidate? Well, there are two choices. You can either hire a candidate or not hire a candidate. Okay, so let's remember this going forward. Now, here's another question. At what point do you stop interviewing? Well, let's say if you have three. If you said, no, I'm not going to interview this person, I'm not going to hire this person. But if you said, yes, I'm going to hire this person, you stop after you hire somebody. So whether it's the first person that you hire or the second person or the third person or the 10th person or so forth, you stop interviewing once you find a suitable candidate for which your outcome is going to be yes, success, you're hired. Okay. So since there's no restriction on the number of interviewees, you assume that there are an uncountably infinite number of people in your waiting room, your pool of candidates, and you consider them in the order that they arrive, for example. Now, each candidate, you can either hire the candidate, that's the hire decision, one outcome, or not hire. So you have two choices, and you stop interviewing when you actually say yes, you make a hiring decision. So let's now line these candidates up. You have the first candidate, and they arrive in order from right to left. So you have candidate 1, followed by candidate 2, followed by candidate 3, and so forth. And you have candidate n minus 1, and then the last candidate n. Now, of course, we're not setting a restriction on n. N is a free variable. And so because we don't say n is 10, n can be anything. It's infinite. And in this case, because it's a sequence of candidates, it's countably infinite. Okay, so we have a countably infinite n number of candidates that we're going to interview. So, of course, for each candidate, candidate 1, there's two choices, hire or not hire. Candidate 2, two choices, hire or not hire. Candidate n minus 1, two choices. Candidate n, two choices. So the n candidates for each, and two choices for each candidate. So if we were to multiply them together, what if we were to say, therefore, 2 times 2 times 2 times 2, n many times, there are 2 to the n choices of success or failure, meaning the hire or no hire, heads or tails decisions. Now, absolutely, there are 2 to the n ways you can assign hire or no hire, but this does not represent, this 2 to the n does not represent the fact that if I decide to hire the second person, I stop interviewing for the third, fourth, fifth, and sixth. So that means there's a particular ordering or particular form of this assignment of success and failure to each one of the slots as we go from right to left, from the first candidate through the nth candidate. So let's examine this. Well, this is not correct. Is there something we're forgetting? What are we forgetting? Well, we are considering all arrangements of hire and no hire when we compute this 2 to the n choices. We're forgetting this ordering that we have. So let's assume there's some candidate, and this is going to be the kth candidate. We're going to mark this kth candidate to be the one that after we interview him or her, we decide to make that hiring decision. So that kth candidate is finally the one that we say, yes, you're a hire, right? You're hired. Okay, so let's think about this number k. The kth is somewhere after the first candidate, could be the first candidate. K is also somewhere before the nth candidate. K could be exactly the nth candidate. So K is what we're going to use to describe that particular candidate where we say hire, right? Now, of course, you wouldn't get to that candidate to say hire unless you've said don't hire, failure for all the candidates up to and before that Kth candidate. So this K is we're going to use to define that candidate that we hire, and the K is going to be somewhere including or after the first, or including or before the nth candidate that's in our waiting room. So if the kth is the one that you hire, is there some property associated with everyone that interviewed before the case? Well, if the case is the one to hire and you stop after you hire the case, that means everyone before the case, you said no hire, don't hire this person. Because if you had said hire for the second candidate, you wouldn't have gotten to the case candidate in order to hire him or her. So there's a structure to this stochasticity that is not represented when you look at all possible assignments of hire, not hire, to each of these n slots representing these interview slots. Okay, so let's think mathematically. How do you express this idea of before the case? Because we need to know how we describe all those candidates before the case, as well as all those candidates we have after the case. So before the case, if we count them, we have a first candidate, second candidate, third candidate, and so forth, up to and including candidate number k minus 1. So that would be the k minus 1th candidate. So mathematically, we express before the case as being k minus 1th. Okay? So what about everyone who interviewed after the case? So we have k plus 1, k plus 2, k plus 3, etc., up to the nth candidate. So we would use k plus 1th to represent mathematically this idea of after the case. So we have the k plus 1th up through the nth candidate as being those after the case. Okay, so we have a failure for everyone from the first up to the k minus 1, because in order to hire the case, that means we did not hire everyone before the case. So that means the k plus 1th, k minus 1th, on through the first, we did not hire. So let's go in order from right to left. For the first candidate, second candidate, third candidate, up through the k minus 1th, we have a failure. We have a no hire. Then we hired the case, so that means we have a success for the case. Now what happens for the k plus 1th? Here's k plus 1th through the nth. Well, it doesn't matter. We don't hire, and it doesn't matter. We stop. Because once we hire someone, they're ready to go, they work, and we don't interview anymore. So those don't matter. We don't even consider them. So let's now look at each candidate's interview as a success or failure outcome. And we said this is a so-called Bernoulli trial. And as a Bernoulli trial, we had the probability of success or hire, that's equal to P, and the probability of failure, no hire, is equal to 1 minus P, that we're also nicknaming Q. Okay, well, the type of distribution that represents this two-way outcome, success or failure, independent of one another, this is exactly a Bernoulli trial, and the outcome, success or failure, corresponds to a Bernoulli distribution. So we're going to make use of a Bernoulli, and this new type of distribution, our geometric, is nothing more than a particular stylized sequence of Bernoulli trials, where we have a bunch of failures ending in a success on the case trial, and then afterwards, k plus 1 to the nth, we don't care about. Okay, so the number k is going to be some outcome, and we want to know when we will have a success, when we're going to have the position of this case person. So this measurement over the observations is this number k, what position is this person in line in the waiting room out of all the people that we're interviewing. And this outcome k, the position of k, is going to be influenced by the stochasticity. So k is going to be the value that a random variable takes on. K is our random variable. Okay, and so what the ask is now is what is the probability that we're going to hire the case candidate in line, given a certain success rate and failure rate. And so for Bernoulli random variable, we know the rate of success. We said the probability of success, or 1, is equal to P. Likewise, what about the rate of failure? We have two outcomes. You could use law of total probability, or just remember the Bernoulli random variable. The probability of failure is 1 minus probability of success, which is 1 minus P, which is 1 minus P, and we're nicknaming that Q. So now's the time to mind your P's and Q's. So we have our sequence of candidates, and we have failure, 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 failure for the first candidate through the k minus 1 candidate. we have a success for the case, and then we don't care about the k plus 1 on through the nth candidate. So if we take all of these failures, this train k minus 1 many failures, followed by a single success, the kth position, we're now going to put the probabilities or associate probabilities with each one of these outcomes. So we have probability 1 minus p, or q, for the first candidate's failure, second candidate's failure, up to including the kth candidate's failure. And then we have our success. That's the rate probability p for the kth candidate in line. Okay, so now we're going to multiply them all together. And so we have one success, ends in success on the kth Bernoulli trial. And then for the k minus 1 Bernoulli trials preceding it, we have how many times? K minus 1 many times we have a failure. Okay, so we write 1 minus p times 1 minus p, k minus 1 many times. We do that product, so that's 1 minus p to the k minus 1 power, because we're multiplying 1 minus p by itself, k minus 1 many times. So we write p, given the success rate of a single trial, the rate at which you will first see a success on the kth trial after all of these k minus 1 many failures leading up to that kth trial. Okay, so we can then substitute our 1 minus p with its nickname q, and we get p times q to the k minus 1 power. And let's model this mathematically. And so what we want to know then is, what is the probability that the first success occurs on the xth trial? Now here we're saying trial number x instead of trial number k. And this x can be unbounded. It's countably infinite. So x could be 1, 2, 3, 4. It can be infinite. Now certainly it can be infinite, but we're interested in the probability that we get that success on trial number x. So going by what we had before, this probability is just p. That's for our success on the xth trial. And then x minus 1 are the trials that we have failure preceding that last trial number x. So that probability that the first success occurs on trial number x, or the xth trial, is just 1 minus p, or q, to the x minus 1 power times p. So here are our x minus 1 failures, and here is our single success. Okay, so you notice we don't use n choose k. We don't say n choose x. And why is that? Well, because the order matters here. The failures must precede the success. We must have all failures up to and including that single success, and we end in success. So that's why we don't do n choose k, because n choose k looks at all possible orderings of that k success, right? You don't say n choose k. You have to have a particular sequence, all failures ending in a single success in that kth position. Okay, this is trickery. This seems really strange because this x can be unbounded. If this x is unbounded, random variable, how can we still have a probability? How's that even possible? I've never heard about unbounded, you might be saying, but it absolutely is true. Now, in order to know if this is an actual probability, remember that we said that the sum of all of the instantiations of a variable, if we add up all the probabilities, that's equal to 1. Well, how can you have something that's infinite, x, and have a probability equal to 1? How does that work? Well, we're going to prove the law of total probability. We're going to say the sum of all the probabilities for each instantiation, x, the xth trial, is equal to 1. So we do this. X, we said, can be infinite. So it can be the first position, second position, third position, up to and including position number infinity. How does that work? We will see. So we have our probability, 1 minus p to the x minus 1 power of failures times p, that single success. And we're going to substitute for p of x this expression. So we get this infinite sum for x goes from 1 to infinity of 1 minus p to the x minus 1 power times p. And this, if we can show that it's equal to 1, yeah, absolutely. This thing behaves like a probability, so it is a probability. So before we do that, we're going to take a brief detour, and we're going to need some tools, in particular, the geometric series. So let's jump in. So this detour, we start with a sequence of terms, and we're going to sum these terms together, and each successive term is going to be obtained by multiplying the previous term by a constant factor. So here's an example geometric series, and that's what a geometric series is defined as. We have 1, and then we follow that with a sum of 1/2. Now, of course, to get from 1 to 1/2, what do? We multiply 1 by 1/2. That gives us 1/2. Now, the next term in this geometric series, that's a sum of terms, is going to be 1/4. We take 1/2, we multiply by 1/2. That gives us the next term, 1/4, and then 1/18, and then 1/16. This is the form of a geometric series. The sum can be infinite. And I'll show to you that even though it sums an infinite number of terms, it does converge to a value. Intuitively, you'll notice the denominator gets smaller and smaller and smaller. Eventually, if you have an infinite number of terms, that goes to 0, the new terms you're summing, and therefore you have a fixed value that you can express in closed form. So it can also be infinite, and let's take a general form. Let's call that constant factor r. Now, in fact, here we have 1. We multiply it by r, we get r. We multiply that r by 1, we get r squared, and r cubed, and etc. Now, of course, if we think about what 1 is, we can say r to the 0 power is equal to 1, right? Anything to the 0 power is 1. And so really, literally, you're multiplying r by exponentiating r to some exponent based on its position. But literally, the relationship between each term and the next in the series is going to be the multiplication of a term. So r to the 0 times r is r to the 1, times r is r to the 2, times r is r to the 3, and so forth. Okay, so you can also, in the full treatment of the geometric series, each term can be multiplied by a scalar, and we'll call that scalar a. So in that case, you have a times r to the 0, that's a, multiplied by r, that's a times r. Multiply that by r, that's ar squared, ar cubed, ar to the 4th, and so forth. And so this form is the full expression of the geometric sequence using variables for some scalar a and some constant factor. We're calling that r. We haven't said what r is. In this example up above, r is equal to 1/2, and a is equal to 1. Okay? All right. So let's continue. So if we were to actually sum this together, we're going to say the sum in compact notation for k goes from 0 to infinity, because we have an infinite number of terms, a times r to the k power. And that's exactly what this is. This is a times r to the 0. So k is equal to 0. This is a times r to the 2 power. So r to the 1 power. So k is equal to 1. This is a times r squared. So k is equal to 2. So this is exactly a compact expression of our geometric sequence in general form. And so what we're going to prove is that this infinite series, this geometric series, if we sum the first n terms, and we didn't set a restriction on n, and then it comes to this expression. And then what we're going to do is take the limit as n approaches infinity to show what this closed form version of this infinite series is, this geometric series. So if we were to sum the first n terms of this geometric series, and we didn't set a restriction on n, we're going to demonstrate that's a times 1 minus r to the n over 1 minus r. So let's do that. So let's rename this sum. We're going to rename it S. We're going to say S is equal to that sum of the first n terms. We have the 0th term, first, second, through the nth minus 1th. That's n terms total, right? N terms. And so we're going to call that S. And now what we're going to do is we're going to multiply both sides of equality here by a constant r. Now, it just happens to be the same r that is involved as that constant factor that defines subsequent terms in the geometric series. But because we have equality, as long as we apply that multiply by r to both sides of equality, the expression is still valid. So let's do that. So if we multiply S times R, we get RS. If we multiply this A times R, we get AR. If we multiply AR times R, it's AR squared. So we have AR squared, AR cubed, AR fourth. And that last term, A times R to the n minus 1, we multiply that by R. That's A times R to the n. So the second expression down below is just this first expression multiplied both sides of equality by that constant factor R. Okay, so now we're going to make an observation. We've kind of lined up the terms, both the original expression and the expression version of expression 1, multiplied both sides of equality by R. We're going to line them up. So we line up the S with the left-hand side with the left-hand side. We line up the first term on the right-hand side with the first term, the second term with the second term, third term with the third term. Now, we'll notice here a little bit of a pattern. You notice here, if we look at the diagonal here, we have AR instead of being AR, if we look diagonally, we have an AR there. If we look at the second expression on the right-hand side of equality, if we look diagonally, we have AR squared there. We have AR cubed here. And then what used to be AR to the n minus 2, after you multiply by R, is going to be AR to the n minus 1. So guess what? AR to the n minus 1. But there's no AR to the n here. That doesn't exist. And likewise, there's no A here in the second expression. So what we're going to do is we're going to subtract these two things. So we're going to take the first expression, S equals that sum, and our second expression, that sum, multiplying both sides of equality by R, and we're going to subtract the second expression from the first expression. So if you do such a subtraction, you can absolutely subtract equations from one another. You're going to subtract the left-hand side from the left-hand side. So the left-hand side of the second expression, you subtract from the left-hand side of the first expression. That's S minus RS. And then you're going to subtract the right-hand side of the second expression from the right-hand side of the first expression. Now, that's where we pay attention to these diagonals. So if you're subtracting this sum from that sum, anytime you subtract something from itself, it goes to 0. So the diagonals here, AR, that's going to go to 0. AR squared minus AR squared, that's going to go to 0. AR cubed minus AR cubed, that's going to go to 0. And then AR n minus 1, AR to the n minus 1, that's going to go to 0. So what do we have left here? We have A, that's left. We have minus AR to the n, that's also left. And so that gives us S minus RS is equal to A minus A times R to the n power. Okay. So now what we can do is we can factor out an S from the terms on the left-hand side of equality. That gives us S times quantity 1 minus R. We factor out an A from the terms on the right-hand side of equality. That gives us A times quantity 1 minus R to the n. So now, then, we can divide. So we're going to divide both sides of equality by 1 minus R. That gives us S is equal to A times 1 minus R to the n over 1 minus R. Oh, wait a minute. That's exactly what we set out to solve. And so this shows that if you have the sum of the first n terms from the 0 to the n minus 1 power here of this sequence, and we didn't define what n is, that sum is equal to A times 1 minus R to the n upon quantity 1 minus R. All right. So, of course, to make this all work, we can't have a denominator that's 0. We're going to set a restriction that says you have to make sure that R cannot be equal to 1, because if R is equal to 1, this becomes 0, and that sum becomes infinity, right? We can't have that. So while it works, oops, something broke. So we're just going to say, don't mind that. We'll just say that R, it works, except for when R is equal to 1. So just set that restriction. Never let R equal to 1. And there are a lot of fix-ups like that all throughout mathematics. All right. So now, let's try this out. Of course, we're going to show now, more generally, that this infinite series, before we said n, if we have the first n terms, we said that's equal to A times 1 minus R to the n over 1 minus R. So we said it's equal to, the sum is equal to A times 1 minus r to the n over 1 minus r. Now that's for the first n terms, and we didn't set a value for what n is. And so we're going to show when you carry this to an infinite series, an infinite number of terms, that means let n get really big, that's going to change to this expression, a times 1 over 1 minus r. Now, of course, this is the case if r, its magnitude is less than 1. And why is that? Because this r to the n here, if you have r to the n and r is less than 1, like 0.1, if you exponentiate something that's less than 1 so many times, if you exponentiate it enough times, it's going to get smaller and smaller and smaller until it goes to 0. And so that r to the n is going to go away if n is big enough and r is less than or equal to 0. So now we have this expression we had before for the first n terms from the 0 to the n minus 1, that's a total of n terms of this geometric series, and we're going to look at what happens when it gets infinitely long instead of just n terms. So one of the things to observe here is a pattern. So you notice here the upper bound of this summation index says n minus 1, and the exponent on r here is n. So the exponent here is 1 more than the upper bound on this summation. That's really important to remember. And so that means if we have a sum of n plus 1 terms from k equals 0 to n, a times r to the k power, we're going to respect that relationship for it all to work out. So here, now we say r to the n plus 1, because that's 1 more than the upper index upper bound of that loop of that summation index. Okay, so now let's assume a is equal to 1, because we just want to show for now that general term. And now we're going to do the part about talking about infinite, because before we talked about first n terms. And we like to say n as the top index, so we're going to modify a little bit. That's why we did this a times 1 minus r to the n plus 1 over 1 minus r if we have our sum going from k equals 0 to n for a r to the k. It's the same expression. We're applying that fact that this exponent is 1 more than the upper bound of this summation index. So what does it mean to have a equal to 1? That's 1 plus r squared plus r cubed. That's our geometric sequence. So that constant factor is r. 1 times r is r times r squared, r third, etc. So now, knowing that we have n terms, right? We have this n as the upper bound in our index. We have the first term up through the nth minus 1 term, and then the nth term, so a total of n plus 1. We're going to take the limit as n goes to infinity, right? So that's talking about the infinite geometric sequence, not just the first n terms. And so that's equal to 1 plus r squared, plus r to the n, right? And then we're going to take the limit, i.e. let n get very, very big, representing an infinite number of terms for our geometric sequence. Okay, so we know that this particular sum in closed form, geometric sequence, is just a times 1 minus r to the n plus 1 power over 1 minus r. So now we're going to take the limit as n goes to infinity. Now, if we take this limit as n goes to infinity, well, if a is equal to 1, that's just 1 minus r to the n plus 1 over 1 minus r, and we're going to take the limit of this expression as n goes to infinity. All right. Now, for r equals 1, what happens? Well, if n gets really, really big and r is less than 1, you're exponentiating something that's getting smaller and smaller and smaller and smaller until it goes to 0. So if r is less than 1, this term is going to go to 0. And that leaves you a limit of 1 over 1 minus r. And so for r less than 1, this infinite geometric series is going to be the sum in closed form, 1 over 1 minus r. Now, of course, what does this have to do with probability and total probability? Well, remember, a probability satisfies this property. A probability, remember, we said some p of x probability is in the range between 0 and 1 on the real number line. And as such, the magnitude of any probability is going to be less than 1. It's at least 0 or more, but it's certainly less than 1. And so we can use this geometric series to show total probability for this expression for the probability mass function for the so-called geometric distribution, the sequence of failures ending in a success. And in fact, the geometric distribution gets its name, geometric, from the fact that we use the geometric series to solve what makes this an actual probability. Okay, and so we're back, and let's go back to where we left off before. And so we're going to model this mathematically, and we had our original probability that we derived based on the interview sequence problem. And we said the probability of X, first success in the X position, the X candidate, or the X trial, or X interview, is 1 minus P to the X minus 1 power times P. So we want to show the law of total probability. We want to show that this infinite sum, because X can go from 0 to infinity, or rather 1 to infinity. You have an infinite number of candidates. So we want to use a geometric sequence to show that this infinite sum is equal to 1. So we want to cast it as a geometric series, which is why we call it the geometric distribution. So let's assume our A value from our geometric series is P, our probability of success. So that's going to be our A. And our 1 minus P, that's going to be our R. And we're going to take the limit as n goes to infinity of this expression. So given our equation from before, we said in the limit, that's just 1 minus R to the n plus 1 over 1 minus R, and we multiplied by A. So we're going to multiply by A, that's our P, okay, we've taken care of that, 1 minus R to the n plus 1. So 1 minus R, this is our R, to the n plus 1 power, over 1 minus R. So that's exactly plugging in for P is our A value for the geometric series, the geometric sum, and 1 minus P is the R value. So now we're going to take the limit as n goes to infinity and see what happens. Well, this is exactly equal to 1. Why is that 1? Because as n gets really, really big, well, 1 minus P is less than 0. Something less is less than 1. 1 minus P is less than 1. Something less than 1 exponentiated a large number of times, that goes to 0. Okay, so 1 minus 1 minus P. So let's take a look at that. That's the same as 1 minus 1 plus P, right? So now we're left with 1 minus 0, that's just 1, times P. And in the denominator, we have 1 minus 1 plus P. Okay, so that 1 minus 1, that goes to 0. We're left with P over P, which is just 1. And here's our answer. So absolutely, if we take this infinite series, the sum of the probabilities for this geometric distribution, we have X minus 1 failures, and the X trial is the single success, where the probability of success is P, the probability of failure is 1 minus P, which we also nickname Q. We use the geometric sum to show that, yep, that is a probability. All of those probabilities add to 1. And so, yes, it is absolutely a probability, and therefore we call it the geometric distribution because it's governed by the geometric series. Okay, so I'm going to end there, and with that, we will pick up next time with our continuation of the development of summary statistics for the geometric distribution. So we'll end there, and I will see you all on Tuesday.